Imagine you're born on a spaceship. Not a spaceship like the ones in movies, no warp drives, no hyperspace, no magic engines that bend the laws of physics. A real one. The best one humanity could build with everything we know right now. It launches the moment you take your first breath. Points toward the stars. And it never stops. You grow up on that ship. You learn to walk, to talk, to read. You fall in love. You grow old. And on the last day of your life, after 80, maybe 90 years of continuous travel at the highest speed that human technology can sustain, you look out the window. Where are you? That's the question this video is going to answer. And the answer is so humbling, so disorienting, so genuinely difficult to absorb, that it changes the way you see everything. The night sky, the stars, the distances between them, and the almost incomprehensible smallness of a human life measured against the scale of the cosmos. We are going to take you on that journey. We'll start by establishing just how vast space actually is, because your intuitions about distance are almost certainly wrong, and we need to correct them before anything else makes sense. Then we'll look at what the fastest possible spacecraft could actually achieve in a human lifetime, with current technology and with the technology that's coming. We'll talk about what happens to the human body and mind during years of space travel, because the universe doesn't just challenge our engines. It challenges our biology, our psychology, and our sanity. We'll explore the physics of time dilation, the genuinely mind-bending consequence of Einstein's relativity that means traveling fast doesn't just get you somewhere faster. It actually slows down your aging relative to everyone you left behind. And we'll look at the most radical ideas for pushing beyond what any single human lifetime can achieve: generation ships, hibernation, and the possibility of uploading consciousness itself. By the end of this video, you will understand exactly how far a human being could travel through space in one lifetime. And you will understand, perhaps for the first time, just how alone we really are out here. Let's go. Before we can answer how far you could travel, we need to confront an uncomfortable truth. You have no idea how big space actually is. Nobody does. Not really. Our brains evolved to navigate a world measured in meters, kilometers, maybe a few thousand kilometers at most. The scale of the universe is so far beyond anything our ancestors ever needed to comprehend that our intuitions are completely useless here. Let's try to fix that. The distance from Earth to the Moon is about 384,000 kilometers. That sounds like a lot, but if you drove there in a car at highway speed, it would take about 5.5 months. Manageable in a painful way. The distance from Earth to the Sun is about 150 million kilometers. At the same highway speed, that's about 170 years. Your great-great-grandchildren might arrive. The distance to the edge of our solar system, roughly where the Voyager probes are now after more than 40 years of travel, is about 23 billion kilometers. Highway speed gets you there in about 26,000 years. And the nearest star to our sun, Proxima Centauri, our closest cosmic neighbor, is 40 trillion kilometers away. 40 trillion. At highway speed, approximately 44 million years. Now here's the part that should genuinely disturb you. Proxima Centauri is our nearest neighbor. The Milky Way galaxy, our galaxy, the one we live in, is about 100,000 light-years across. That means light itself, traveling at 300,000 kilometers per second, takes 100,000 years to cross it. And the observable universe contains roughly 2 trillion galaxies, spread across 93 billion light-years. Your entire life, every experience, every relationship, every moment, happens in a tiny corner of one unremarkable galaxy. In a universe so vast that the numbers describing it have stopped meaning anything to human minds. That's the playing field. Now let's see what we can do with it. There is a speed limit in this universe. Not a legal one, a physical one. Baked into the structure of reality by the same equations that gave us nuclear energy, GPS satellites, and everything else that modern physics has produced. And that speed limit is the speed of light. Approximately 299,792 kilometers per second. Nothing with mass can reach it. The faster you go, the more energy it takes to accelerate further. And as you approach the speed of light, the energy required approaches infinity. You would need infinite fuel to reach the speed of light, which means you can get very close but never there. This is not a technological limitation that future engineering will solve. It is a fundamental feature of space-time. Einstein's special relativity is one of the most tested theories in the history of science, and it has never been wrong. The speed of light is the universal speed limit, and it applies to everything: matter, information, causality itself. What this means for space travel is brutal. Even if you somehow built a spacecraft that could travel at, say, 10% of the speed of light, a speed utterly beyond anything we have ever achieved, it would still take 43 years to reach Proxima Centauri. One way, with no way to slow down unless you brought fuel for that too. At 1% of light speed, still thousands of times faster than anything we've built, the journey takes 430 years. Longer than the United States has existed as a country. The universe is not just big. It is big in a way that specifically defeats the one thing that makes us feel like we can conquer distances: speed. We can go faster. We can go much faster than we go now. But we cannot go fast enough. Not even close. Here's something worth sitting with. When we ask how far you could travel in a lifetime, what exactly is a lifetime? The average global life expectancy is currently around 73 years. In wealthy countries with advanced healthcare, it's closer to 80 or 85. Some researchers believe that within the coming decades, medical advances could push that significantly higher, perhaps past 100, perhaps further. But in space, lifetime gets complicated very quickly, because space is trying to kill you in ways that Earth never does. Cosmic radiation is the most immediate problem. Outside Earth's protective magnetic field and atmosphere, you are exposed to a constant bombardment of high-energy particles from the sun and from deep space. Particles that damage DNA, increase cancer risk dramatically, and may cause long-term neurological effects. Current estimates suggest that a round trip to Mars, just Mars, our nearest planetary neighbor, would expose astronauts to radiation levels that significantly exceed NASA's current career limits. Beyond radiation, there's microgravity, the absence of the gravitational force your body evolved under. Without gravity, bones lose density, muscles atrophy, the cardiovascular system changes. Fluid shifts toward the head, causing vision problems that have affected a significant proportion of long-duration astronauts on the International Space Station. And then there's the psychology, the isolation, the confinement, the inability to go outside, to feel wind, to see a horizon. Astronauts on 6-month ISS missions report significant psychological strain. A journey measured in decades would present challenges that we have never had to seriously grapple with. So when we ask how far in a lifetime, we're not just asking about physics. We're asking about biology, medicine, psychology, and engineering all at once. The answer is limited not just by the size of the universe, but by the fragility of the beings trying to cross it. Let's ground ourselves in what humanity has actually achieved, because it's simultaneously impressive and humbling. The moon is the farthest any human being has ever traveled from Earth. 12 people walked on it between 1969 and 1972. The journey took about 3 days each way. In cosmic terms, the moon is so close to Earth that it barely registers. It's like walking to the end of your driveway and declaring you've explored the neighborhood. No human has gone further. In the more than 50 years since Apollo 17, the farthest humans have traveled from Earth is the distance to the International Space Station, about 400 kilometers up. We went to the moon and then, for half a century, we stopped going anywhere. Mars is the obvious next destination, the one that NASA, SpaceX, and space agencies around the world are working toward. At its closest approach to Earth, Mars is about 54 million kilometers away. A journey there with current technology would take roughly 7 to 9 months. But here's the catch. Because of the orbital mechanics of Earth and Mars around the Sun, you can't just leave whenever you want. Launch windows open only every 26 months, which means if you go to Mars, you're waiting there for about 18 months before the planets align for a return trip. The total mission duration, roughly 2 to 3 years. Beyond Mars, the distances explode. Jupiter is about 600 million kilometers from Earth at closest approach. Saturn over 1 billion. Uranus and Neptune further still. The New Horizons probe, which flew past Pluto in 2015, took 9.5 years to get there, traveling at about 58,000 kilometers per hour. That's genuinely fast by human standards. In cosmic terms, it's a gentle stroll. The most distant human-made objects in existence are the Voyager probes Voyager 1 and Voyager 2, launched in 1977. They are the only human artifacts to have entered interstellar space. The region beyond the Sun's sphere of influence, where the solar wind gives way to the interstellar medium. Voyager 1, the farther of the two, is currently about 23 billion kilometers from Earth. It has been traveling for over 47 years at about 17 kilometers per second, roughly 61,000 kilometers per hour, and it is still in our cosmic backyard. At its current speed, it would take about 73,000 years to reach Proxima Centauri. Think about that. The fastest object humanity has ever launched, traveling continuously for 47 years. And it would need another 73,000 years to reach our nearest stellar neighbor. One probe, one star, 73,000 years. The Voyager probes were not designed to go to another star. They were planetary science missions that happened to achieve escape velocity from the solar system. But they give us a baseline, a concrete, real-world data point for what current technology achieves over a human-relevant timescale. In 47 years of travel, Voyager 1 has covered about 0.002% of the distance to Proxima Centauri. In an entire human lifetime of travel at Voyager speed from birth to death, you would cover roughly 0.004% of that distance. You would die having barely left the solar system. This is where we are. This is the starting point. The question is, how much better can we do? There's a detail about space travel that doesn't get enough attention. The solar system is enormous. We talk about leaving the solar system as if it's a doorway you step through on your way to the stars. It isn't. It's a journey in itself. The sun's gravitational influence extends roughly 2 light-years in every direction. A region called the Oort cloud, a vast shell of icy objects that marks the very outer edge of what we consider our solar system. 2 light-years. Light takes 2 years to cross it. Voyager 1, after 47 years of travel, has barely entered the inner edge of this region. To cross the entire solar system, from the Sun to the outer edge of the Oort cloud, at Voyager speed would take approximately 30,000 years. Not to reach another star, just to exit our own system. This is the first wall. Before we can even begin talking about interstellar travel, we have to solve the problem of crossing our own solar backyard. And our backyard is, by cosmic standards, tiny. The engineering challenge is immense. You need fuel, vast amounts of it, to accelerate to useful speeds and then to decelerate at your destination. The fuel itself has mass, which means you need more fuel to accelerate the fuel, which adds more mass, which requires more fuel. This is the Tsiolkovsky rocket equation, and it is merciless. The faster you want to go and the farther you want to travel, the exponentially more propellant you need, to the point where chemical rockets become completely impractical for interstellar distances. Something fundamentally different is required. And that's where things get interesting. Of all the ways space can kill you, radiation is the most insidious. You can't see it, feel it, or smell it. But from the moment you leave Earth's protective magnetic field, it is working on you quietly, relentlessly at the cellular level. Earth's magnetic field deflects the most dangerous particles from the sun and from deep space. Outside that shield, you are exposed to 2 main sources of radiation. Solar energetic particles, which are bursts of radiation from solar flares and coronal mass ejections, and galactic cosmic rays, high-energy particles, mostly protons, accelerated by distant supernovae and other cosmic events to velocities approaching the speed of light. Galactic cosmic rays are particularly dangerous because they are nearly impossible to shield against. They are so energetic that they can penetrate almost any material, even thick lead shielding. They don't just pass through your body harmlessly. They interact with your DNA, breaking chemical bonds, causing mutations, triggering cell death. Over months and years of exposure, the cumulative damage increases the risk of cancer significantly and may cause damage to the central nervous system, affecting memory, cognition, and behavior. NASA has calculated that a round trip to Mars, roughly 2 to 3 years, would expose astronauts to radiation doses that approach or exceed the agency's career limits for radiation exposure. And Mars is just next door. A journey to another star system, even at the fastest speed we can realistically contemplate, would take decades. The radiation exposure over that period would be catastrophic by current standards. Solutions exist in principle. Magnetic shielding, generating an artificial magnetic field around the spacecraft to deflect charged particles, is theoretically possible but would require enormous amounts of power and engineering we don't yet have. Water shielding works against some types of radiation. Pharmacological interventions, drugs that repair DNA damage or protect cells, are being researched. But none of these is sufficient on its own, and the problem of radiation remains one of the hardest unsolved challenges in long-duration space travel. The human body is a masterpiece of engineering for living on Earth. It is spectacularly poorly designed for anywhere else. Every system in your body evolved under the assumption that gravity would be pulling on it, constantly, at 9.8 meters per second squared. Your bones are dense because they need to support your weight. Your heart pumps blood upward against gravity. Your muscles are sized to move a body that has weight. Your inner ear evolved to sense which way is down. Remove gravity, and all of those systems start to malfunction. Bone loss in microgravity is rapid and significant. Astronauts on the International Space Station lose roughly 1 to 2% of their bone density per month in the lower body, a rate that would leave a long-duration space traveler with severely compromised skeletal structure after a few years. Resistance exercise can slow this, but not stop it. Over decades, the cumulative loss would be severe. Muscle atrophy follows the same pattern. Without the constant demand of supporting body weight and moving against gravity, muscles shrink. The heart, a muscle that pumps against gravitational resistance, changes shape and function. Cardiovascular fitness degrades even in astronauts who exercise vigorously every day. And then there's the vision problem, one of the most alarming discoveries of recent space medicine research. A significant proportion of astronauts who spend 6 months on the ISS return with measurably degraded vision. The cause appears to be intracranial pressure. In microgravity, fluid that normally stays in the lower body shifts upward, increasing pressure in the skull. This pressure pushes on the back of the eyeballs, distorting their shape and changing the focal length of the eye. For a mission lasting decades, the implications of all these effects are sobering. You would arrive, if you arrived, as a fundamentally different physical specimen than the one that departed. Weaker bones, diminished muscles, possibly compromised vision and cognition. The universe would have taken its toll. The body is not the only thing space breaks down. The mind has its own vulnerabilities, and the psychological demands of long-duration space travel may be the hardest challenge of all. Consider what you would be giving up. A view that changes. Seasons. The feel of wind. The smell of rain. Random encounters with strangers. The texture of grass under your feet. The ability to go somewhere, anywhere, that isn't the inside of a metal cylinder hurtling through an absolute void. Research on isolated, confined environments, Antarctic research stations, submarine deployments, simulated Mars missions, consistently shows that psychological strain increases significantly with duration. People become irritable, depressed, anxious. Sleep disrupts. Interpersonal conflicts intensify. The phenomenon called third-quarter syndrome, a spike in psychological difficulty roughly 3/4 of the way through a long mission, has been observed across multiple studies. And those missions last months, not decades. The psychological profile of someone who has spent 20 or 30 years in a spacecraft, who has grown up there, who has never felt sunlight on their skin or stood in an open space, is something we have never encountered and can barely model. Russian cosmonaut Valery Polyakov holds the record for the longest single spaceflight, 437 days on the Mir space station. He returned to Earth showing remarkable psychological resilience, but he also returned to Earth. He knew it was finite. He knew what was waiting for him. A crew heading to another star would have no such comfort. They would know that their destination is decades away, that everyone they knew on Earth will die before they arrive, that they may never set foot on a planet again. The psychological design of a generation ship, the social structures, the purpose, the meaning-making might be more important than any of its engines. Let's do the calculation that the title of this video promises. With the best propulsion technology we actually have right now, or could realistically build in the near term, how far could you travel in a human lifetime? The fastest spacecraft ever built is the Parker Solar Probe, which in late 2024 reached speeds of approximately 690,000 kilometers per hour during its close approaches to the Sun. That's about 0.064% of the speed of light. Extraordinary by human standards. Negligible by cosmic ones. At that speed, sustained continuously for 80 years, you would travel approximately 484 billion kilometers. That's about 51 light hours. Or to put it another way, roughly 3 times the distance from the Sun to Neptune. In 80 years of travel at the fastest speed any human object has ever reached, you would cover a distance that light crosses in about 2 days. You would still be well within our solar system. You would not even be close to the Oort cloud. You would not have taken a single meaningful step toward the nearest star. Now let's be more generous and consider near-future propulsion concepts. Ion thrusters, already used on some spacecraft, are more efficient than chemical rockets and can accelerate continuously over long periods, reaching higher speeds. Nuclear thermal propulsion, which NASA and DARPA are actively developing, could achieve exhaust velocities several times higher than chemical rockets. With nuclear thermal propulsion, a spacecraft might realistically reach speeds of around 100,000 to 200,000 kilometers per hour, 2 to 3 times faster than Voyager. At 200,000 kilometers per hour for 80 years, you travel about 140 billion kilometers. Still less than 0.015 light-years. Still nowhere near another star. The numbers are brutal. With foreseeable technology, a human lifetime of travel gets you out of the solar system barely but nowhere near the stars. The nearest stellar system remains essentially unreachable in a single human life with anything like current propulsion. Now let's push further into the realm of technology that is theoretically possible, physically sound, but not yet built. Because the gap between where we are and where we need to be is so enormous that conventional propulsion improvements won't bridge it. We need something fundamentally different. Nuclear pulse propulsion is perhaps the most audacious concept ever seriously studied by engineers. Project Orion, developed in the 1950s and 1960s by scientists including Freeman Dyson, proposed a spacecraft propelled by a series of nuclear explosions detonated behind it. Each explosion pushes a massive pusher plate, which absorbs the shock and transfers momentum to the spacecraft. The numbers are extraordinary. An Orion-type spacecraft could theoretically reach speeds of 3 to 10% of the speed of light, 10 to 30 times faster than any vehicle we've ever built. At 10% of light speed for 80 years, you travel 8 light-years. That puts you past Proxima Centauri, past the Alpha Centauri system, and in the vicinity of Barnard's star. You would have reached another star system. In one lifetime, without time dilation effects playing a major role at this speed, you would arrive as a very old person, but you would arrive. Laser sail propulsion, the concept behind the Breakthrough Starshot initiative, takes a different approach. Instead of carrying fuel, a sail spacecraft uses a powerful laser array on Earth to push a lightweight sail to high speeds. Breakthrough Starshot's goal is to accelerate a gram-scale probe to 20% of light speed using a gigawatt-scale laser array. A crude version would need to be far larger and would face enormous challenges. But the concept is physically sound. Solar sails, using the actual pressure of sunlight rather than lasers, are already being tested. They're slow but require no fuel. Over very long periods, with the right initial boost, they could reach useful interstellar speeds. None of these technologies is ready. None of them is close to being ready for crewed missions. But none of them violates physics. They are genuinely possible. And if humanity invested seriously in any of them, the timeline to another star could shrink from the impossible to the merely very hard. Here's where physics gives us something unexpected and genuinely strange. Einstein's special relativity predicts that time passes differently for objects moving at different speeds. The faster you move, the more slowly time passes for you relative to someone who is stationary. This is not a theoretical curiosity. It has been measured directly with atomic clocks on aircraft and satellites, and it matches the predictions of relativity precisely. For everyday speeds, the effect is negligible. But as you approach the speed of light, it becomes dramatic. This is the famous twin paradox. One twin stays on Earth. The other travels to a distant star at close to the speed of light and returns. When they reunite, the traveling twin is younger, sometimes dramatically younger, than the one who stayed home. Not because of any biological effect of space travel. Simply because time itself passed more slowly for the traveler. At 10% of the speed of light, the time dilation effect is small, You age about 0.5% more slowly than someone on Earth. Over an 80-year journey, that's about 5 months difference. Interesting, but not transformative. But at 90% of the speed of light, the effect is profound. Time for the traveler passes at about 44% of the rate it passes on Earth. An 80-year journey by the traveler's clock would correspond to about 180 years of Earth time. The traveler arrives having aged 80 years. Everyone they knew on Earth has been dead for a century. And at 99% of the speed of light, time dilation factor of about 7. A subjective journey of 80 years corresponds to 560 years of Earth time. The traveler could cross more than 500 light-years of distance in their own subjective lifetime, arriving at a destination 500 light-years away while having aged only 80 years. Time dilation is the loophole. It doesn't let you travel faster than light, but it lets you experience less time during the journey. The universe stays just as large, but your personal experience of crossing it can be compressed, if you can get close enough to light speed. To understand time dilation, you need to let go of something that feels completely obvious. The idea that time flows at the same rate for everyone, everywhere, always. That a second here is the same as a second there. That when you say, right now, there's a universal now that everyone shares. None of that is true. Einstein showed, in 1905, that time is not a fixed background against which events occur. It is a dimension like space, and it can be stretched and compressed depending on how fast you're moving and how strong the gravitational field around you is. The core insight of special relativity is that the speed of light is the same for all observers, regardless of their motion. This sounds innocuous. Its implications are not. If the speed of light is constant, and if speed is distance divided by time, then for different observers measuring the same light, either distance or time or both must be different. Einstein followed this logic to its conclusion. Time and space are not separate, absolute things. They are aspects of a single four-dimensional fabric spacetime that bends, stretches, and compresses depending on motion and gravity. The experimental evidence for this is overwhelming. GPS satellites have to correct for relativistic time dilation, both from their speed and from the weaker gravity at their altitude, or the navigation system would accumulate errors of kilometers per day. Every time you use GPS, you are benefiting from a technology that only works because Einstein was right about time. For space travel, the implications are profound. Time dilation means that a traveler moving at relativistic speeds, close to the speed of light, experiences less time than a stationary observer. The journey that takes 500 years from Earth's perspective might take only 50 years from the traveler's. The universe doesn't shrink, but the traveler's subjective experience of crossing it does. Let's make the numbers concrete, because the abstract principle becomes genuinely staggering when you attach real numbers to it. At 50% of light speed, the time dilation factor is about 1.15. For every year experienced by the traveler, 1.15 years pass on Earth. Not dramatic but measurable. At 90% of light speed, factor of 2.3, the traveler ages 1 year for every 2.3 years on Earth. At 99% of light speed, factor of 7.1. 1 year of travel corresponds to 7 years on Earth. At 99.9% of light speed, factor of 22. 1 year of travel, 22 years on Earth. At 99.99% of light speed, factor of 71. 1 year, 71 years. At 99.9999% of light speed, factor of 707. 1 year of the traveler's life, 707 years on Earth. Do you see where this is going? If you could somehow travel at 99.9999% of the speed of light, a speed that would require energy inputs we cannot currently imagine, you could cross the entire Milky Way galaxy 100,000 light-years wide in about 141 years of subjective time. You would age 141 years. On Earth, 100,000 years would have passed. You could, in a single human lifetime of subjective experience, travel to essentially any destination in the observable universe. The catch: everyone and everything you knew would be dead and gone, replaced by civilizations you could not recognize, by a future you could not have imagined. You would arrive utterly alone, in a universe that has moved on without you. Time dilation offers reach at the cost of connection. You can go anywhere, but you can never go back to the world you left. Let's do the definitive calculation for the scenario that represents the outer limit of what might be physically achievable for a crewed spacecraft. Not today, not in a century, but perhaps in the far future of human technology. At 99% of the speed of light, with a time dilation factor of approximately 7, a traveler who lives 80 subjective years could cover roughly 560 light-years of distance. Not 560 light-years of subjective distance, 560 actual light-years of the real universe, compressed into 80 years of personal experience. 560 light-years puts you well outside our immediate stellar neighborhood. Within that radius from Earth, there are thousands of star systems. Some of those systems contain planets in the habitable zone of their stars. Some of those planets may have atmospheres suggesting the presence of liquid water. A few have already been identified as candidates worth studying. The exoplanet Kepler 442b, for instance, is about 1,200 light-years away, just beyond the reach of this scenario. Kepler 22b, at 620 light-years, is tantalizing close to the limit. The TRAPPIST-1 system, which contains multiple potentially habitable planets, is about 40 light-years away, well within reach. At 99% of light speed in one human lifetime, you could reach TRAPPIST-1 in about 6 years of subjective time. You could explore its planets, 3 of which are in the habitable zone, and perhaps send back a signal. That signal would take 40 years to reach Earth. By the time anyone received it, you would be long gone, continuing your journey. This is the vision, not the reality. We are nowhere near 99% of light speed, and the energy required to reach it is incomprehensible with current understanding. But physics permits it, and physics is the only permission that ultimately matters. If we can't get close to the speed of light, and for the foreseeable future we almost certainly can't, then perhaps the answer to interstellar travel is not to go faster. Perhaps the answer is to accept the journey's length and design human civilization to survive it. This is the concept of the generation ship, a spacecraft so large, so self-sufficient, and so carefully designed that it can sustain a human population across multiple generations. The people who launch the ship are not the people who arrive. They are the ancestors of the arrivals. The journey is not something any individual undertakes. It is something a community undertakes across centuries. The engineering requirements are staggering. The ship would need to be large enough to support a genetically viable human population. Population geneticists suggest a minimum of around 500 people, though larger is better, to avoid the problems of inbreeding and genetic drift over centuries. It would need to produce its own food through closed-loop agriculture, recycle all water and air, generate its own power, likely through nuclear fission or fusion, maintain itself structurally across centuries without access to external resources. It would need to be, in essence, a world. A small, controlled, artificial world, but a complete one, with space for agriculture, for recreation, for social life, for culture, with hospitals, schools, libraries, with everything a human society needs not just to survive, but to remain psychologically healthy across generations. At a speed of 0.1% of light speed, ambitious but perhaps achievable with nuclear propulsion, a generation ship would take about 4,300 years to reach Proxima Centauri. At 1% of light speed, roughly 430 years. At 10%, about 43 years, potentially within a single generation, if the technology could be achieved. The engineering is the easy part. The hard part is the humans. Here is the ethical question that the generation ship concept forces us to confront, and it is one of the most uncomfortable in all of space exploration philosophy. Do the people born on the ship consent to being there? The founding generation makes a choice. They volunteer. They sign up. They know what they're committing to, but their children don't. Their grandchildren don't. The people who live their entire lives in the middle of the journey, born into a metal world, growing up under artificial light, knowing that they will die before the ship arrives. They never chose this. They were born into it. Is that ethical? Some philosophers argue that it is not fundamentally different from the situation of everyone who has ever lived. We are all born into circumstances we didn't choose, in societies and situations we had no say in. Others argue that deliberately bringing people into existence in conditions of radical confinement and certain lifetime limitation is categorically different from ordinary human birth. The psychological reality of mid-journey generations is something we can only speculate about. These would be people who know, from childhood, that they will never see a planet, never feel natural sunlight, never stand on ground that stretches to a horizon. Their entire cosmos is the ship. Their entire history is the journey. Their entire future, the destination, is something their children or grandchildren will experience. Would they find meaning? Would they develop a culture, an identity, a sense of purpose rooted in the journey rather than the destination? History suggests that humans are remarkably good at finding meaning in the circumstances they're given. But history has no examples of circumstances quite like this. The generation ship is not just an engineering problem. It is a civilization problem, and civilizations are complicated, fragile, and very hard to design. Let's go deeper into the ethics because they deserve serious treatment. A generation ship would require, more than any other human institution, a sense of shared purpose that persists across centuries. The founding generation's motivation is clear. They chose this, they believe in the mission, they are driven by the pioneer spirit and the knowledge of what they are sacrificing. But how do you transmit that motivation across 10 generations? How do you ensure that the great-great-great-grandchildren of the founders still believe in the mission, still maintain the ship, still want to arrive? History gives us cautionary examples. Religious communities that set off with intense shared purpose often fragment within generations as the original vision dilutes. Political movements that seemed monolithic at their founding often diverge into factions. Institutions built to last centuries routinely fail to. The generation ship would need social engineering of a kind never before attempted, or it would need to accept that social drift will occur and build in resilience against it. There's also the problem of arrival. After hundreds of years in transit, the arriving generation lands on an alien world. A world nothing like the ship that is the only home they've ever known. They've grown up in controlled, known, safe environments. Now they must colonize an unknown planet. One that may have extreme weather, unfamiliar biology, unpredictable geology. The psychological whiplash of that transition, from the total control of a ship to the radical uncertainty of a new world, could be devastating. None of this means generation ships are impossible or unethical. But it means they are not just an engineering project. They are a project in social design, psychology, ethics, and the deepest questions of what humans owe to the people they bring into existence. The most elegant solution to the problems of long-duration space travel, the radiation, the psychological strain, the social complexity of generation ships, is also the one most associated with science fiction. Put the crew to sleep for the journey. If you could suspend a human being in a state of dramatically reduced metabolism, slowing the heartbeat, dropping the body temperature, essentially pausing the biological processes of aging, you could cross decades or centuries of travel without the crew experiencing much of it. They would wake up at the destination, having aged perhaps months instead of decades. This is not as far-fetched as it might seem. Therapeutic hypothermia, cooling patients to slow metabolism and protect against brain damage during cardiac arrest, is already standard medical practice. Certain animals achieve something like natural hibernation, dramatically reducing their metabolic rate for months at a time. Some species can survive extreme desiccation, essentially suspending all biological activity, and revive when conditions improve. The challenge for human hibernation is that the human body is not designed for it. We don't have the cellular machinery to survive being cooled to the temperatures that would most dramatically slow metabolism. Ice crystals form in cells and destroy them. The liver and kidneys don't tolerate extreme cold well. And waking from deep hypothermia carries its own risks. Research is ongoing. NASA has funded studies into torpor, a mild form of metabolic suppression that might be achievable in humans without the extreme risks of full cryogenic suspension. Some biotechnology companies are working on pharmacological approaches, drugs that could induce a hibernation-like state. The science is early and the challenges are significant, but the basic concept is not forbidden by biology. Animals do versions of it. The question is whether humans can be engineered to do it too. If human hibernation became possible, the calculus of space travel would change dramatically. A journey of 50 years ship time could be experienced as months. The psychological burden of confinement would be minimized. The social complexity of generation ships would be avoided, and the radiation exposure, while still occurring to the sleeping body, might be manageable if the hibernating state also reduced cellular sensitivity to radiation damage. In 1994, Mexican physicist Miguel Alcubierre published a paper that made physicists sit up and pay very close attention. He described a solution to Einstein's field equations, the mathematical heart of general relativity, that would allow, in principle, a spacecraft to travel faster than light without violating the laws of physics. The trick: you don't move the spacecraft faster than light. You warp space itself. In Alcubierre's metric, a bubble of flat spacetime surrounds the spacecraft. In front of the bubble, space is compressed, contracted. Behind it, space is expanded. The spacecraft rides this wave of spacetime distortion the way a surfer rides a wave, without moving relative to the space immediately around it, but with that space itself moving through the larger universe at superluminal speeds. Since the spacecraft isn't moving through space, but moving with space, the special relativity prohibition on exceeding light speed doesn't apply. Locally, the spacecraft is stationary. Globally, it is moving faster than light. The problems are significant. The original Alcubierre metric required exotic matter with negative energy density, in amounts that exceeded the mass energy of the planet Jupiter. That's not a technology problem. It's a we have no idea if this stuff exists problem. Subsequent research has suggested modifications that might reduce the exotic matter requirements dramatically, but the theoretical work is still ongoing. More recently, in 2021, physicist Eric Lentz proposed a version of warp drive that might not require exotic matter at all, using conventional positive energy configurations. The energy requirements are still enormous, but the exotic matter problem might be solvable. This is very early theoretical work, and it has not been peer-reviewed to the point of broad acceptance. But it is a sign that serious physicists are still engaged with this idea. A working warp drive would change everything. The entire discussion of lifetimes and distances becomes irrelevant. Any point in the universe becomes reachable in any amount of time the technology allows. But we are very far from knowing whether it is possible, and further still from building one. And now we reach the most radical possibility of all, one that sidesteps the biological limitations of space travel entirely by questioning whether biological travel is necessary at all. What if, instead of sending bodies through space, we sent minds? The concept of mind uploading, transferring the information content of a human brain into a digital substrate, is currently science fiction. We don't know if consciousness is substrate independent. We don't know if a digital copy of a brain would have genuine experiences or simply simulate having them. We don't know if the original person would survive the transfer or simply be replaced by a copy. These are among the deepest unsolved problems in the philosophy of mind. But from a pure engineering standpoint, a digital mind would have enormous advantages for space travel. It wouldn't need air, food, water, or warmth. It wouldn't be damaged by radiation in the way biological tissue is. It could be transmitted as a signal at the speed of light, rather than carried physically across space. And it could be paused during transit, experiencing no subjective time at all during the journey, and resumed upon arrival. A signal traveling at the speed of light could reach Proxima Centauri in 4.2 years. A digital mind sent as that signal would experience no subjective time during travel. It would be transmitted and received, with no experience of the intervening years. From the mind's perspective, the journey would be instantaneous. The destination would need the infrastructure to receive and run the uploaded mind, which means either sending physical infrastructure ahead, or finding that someone has already built it there. But if the technical and philosophical problems were solved, the constraint of lifetime would become irrelevant. You could send your mind to any star in the galaxy and arrive, in a sense, immediately. Whether what arrives would still be you is a question that gets at the deepest mysteries of personal identity and consciousness, the same mysteries that make the simulation theory and the nature of death so hard to resolve. We are back at the edges of space travel at the same fundamental questions about what we are. If we were to actually attempt an interstellar journey in the foreseeable future, Proxima Centauri is the obvious first destination. It is the closest star to the Sun, 4.24 light-years away, and we know it has at least one planet. Proxima Centauri b, discovered in 2016, orbits within the habitable zone of its star, the region where liquid water could exist on the surface. It is roughly Earth-sized. For a moment, this sounds exciting, but the details are sobering. Proxima Centauri is a red dwarf, a star much smaller, cooler, and dimmer than our Sun. It is also extremely active, producing frequent and intense flares that blast its planets with radiation far more severe than Earth ever receives from the Sun. A planet in the habitable zone of a red dwarf is so close to the star that it is almost certainly tidally locked. One face permanently toward the star, the other permanently in darkness. The radiation environment, the tidal locking, and the atmospheric implications of frequent flares make Proxima Centauri be a challenging candidate for habitability, despite its favorable orbital position. The Alpha Centauri system, which Proxima orbits at a great distance, contains two Sun-like stars, Alpha Centauri A and B. These are more promising stellar hosts. No confirmed planets have been found around them yet, but searches are ongoing. A planet around Alpha Centauri A or B in the habitable zone would be a far more Earth-like prospect than Proxima B. The point is, our nearest neighbors are right there, for 0.24 light-years. Close enough that, with sufficient technology and sufficient willingness to commit, a crewed mission is imaginable within the next few centuries. Not easy, not safe, not cheap, but imaginable. Beyond the Alpha Centauri system, the catalog of potentially habitable exoplanets has exploded in recent years, driven by the Kepler Space Telescope and its successors. We now know of thousands of confirmed exoplanets and thousands more candidates, scattered across the sky at distances from a handful of light-years to thousands. The TRAPPIST-1 system, 40 light-years away, is perhaps the most exciting nearby candidate. It contains 7 Earth-sized planets, 3 of which are in the habitable zone of their star. The system has been studied intensively since its discovery, and the James Webb Space Telescope has begun analyzing the atmospheres of its planets. Early results have been cautious but not discouraging. At 40 light-years, TRAPPIST-1 is within reach of a nuclear propulsion spacecraft, not in a single human lifetime at current technology, but in a few centuries of ship time at speeds achievable with near-future propulsion. With time dilation at relativistic speeds, it becomes reachable in a subjective human lifetime. Tau Ceti, about 12 light-years away, is a Sun-like star with evidence of multiple planets, some potentially in the habitable zone. Epsilon Eridani, 10.5 light-years distant, is a young Sun-like star with a disk structure suggesting active planetary system formation. The galaxy, it turns out, is full of potentially interesting destinations within a few dozen light-years. The challenge is not finding somewhere to go. The challenge is getting there. And that challenge is purely one of physics and engineering, not of the universe withholding possibilities. And here, at the end of this journey, we need to sit with something difficult. Even with warp drives and uploaded minds and generation ships and relativistic travel, even with every technology we can currently imagine, the vast majority of the universe is permanently beyond our reach. Not just beyond the reach of a single human lifetime, beyond the reach of our entire civilization, for as long as it might exist. The observable universe is 93 billion light-years across, contains 2 trillion galaxies. Even traveling at the speed of light continuously, you could not reach most of those galaxies in the age of the universe, because the universe is expanding, and the most distant galaxies are receding from us faster than light can cross the gap. They are not just far. They are unreachable in principle. Even within our own galaxy, a civilization limited to subliminal travel, and all the evidence suggests that's what we are, can only ever access a fraction of the Milky Way's 100,000 light-year span within any humanly relevant time frame. How do we live with that? One answer is, the same way we live with mortality. The universe doesn't owe us access to all of itself, any more than life owes us immortality. The frontier being finite doesn't make it less worth exploring. Proxima Centauri is 4.2 light-years away and possibly harbors a planet. That is extraordinary. The TRAPPIST-1 system is 40 light-years away and has 3 potentially habitable worlds. That is extraordinary. The portion of the cosmos that is, in principle, accessible to a sufficiently advanced version of our civilization is enormous beyond comprehension, even if it is not infinite. The question was, how far could you travel through space before you die? With current technology, you'd barely leave the solar system. With near-future technology, you might reach the edge of the solar system and a little beyond. With the most optimistic foreseeable propulsion, you might reach the nearest stars. With relativistic travel, you could reach thousands of star systems. With technologies we can barely imagine, the galaxy itself might be crossable in a single subjective lifetime. But in every scenario, the universe is larger than the reach. The horizon always extends beyond the traveler. The cosmos is not a puzzle to be solved or a territory to be conquered. It is something to be explored, step by step, generation by generation, with patience and humility and the kind of wonder that doesn't require reaching the end to find meaning in the journey. You will die before you get very far. So will the next generation, and the one after that. But we will keep going, because that's what we do. And every light year crossed is one that no human has crossed before. That has to be enough. And somehow, when you really think about it, it is.